Good morning. This is the 16th lecture of lecture series on X-ray crystallography and solid state chemistry. Here we have been talking about data collection, how we collect data from powder samples. So we talked about device share camera, linear focusing camera, and also diffractometer, X-ray powder diffractometer. The A is a sample of device share camera, where exposure time is 3 hours of the same sample. We took silicon as the sample, powder silicon sample. B, it's a linear focusing cameras data, and C, that same sample, we took it in diffractometer. So it is very important that when we analyze X-ray powder diffraction data, that data should be of quality, high quality. And that depends on how your sample are prepared. And in many cases, we see that the samples are not properly prepared, and therefore crystalline size, etc., are not uniform. Therefore, we do not get a proper quality data. We will talk about quality data later. Well, we say X-ray powder pattern of a solid material is its fingerprint, like our fingerprints that we characterize a person with his fingerprint. So X-ray powder pattern is the fingerprint of a solid material. There are two main factors to determine X-ray powder patterns. The first one is the size of the unit cell. And the second one, the atomic number and position of the atoms in the unit cell. We have discussed about unit cell, we have discussed space group, and we talked about atomic position in space group also. So these are the factors which will dictate the X-ray powder pattern. So we can have two materials having the same crystal structure, and then we will see that the powder patterns are different. For example, we are talking about potassium fluoride, potassium chloride, and potassium iodide. The cell parameters of potassium fluoride is 5.347 angstrom, whereas calcium chloride is 6.2931 angstrom, and potassium iodide 7.0655 angstrom. Okay, so you can see that all these three are having rock salt structure, but then the unit cells are different. And thereby, the powder pattern is position, and also the intensity is different. One can see it here very clearly. These are the HKL value. It means planes, different planes in the sample. And then this is the D values with angstrom. And that is the arbitrary, I would say not so arbitrary, intensity of this plane. So you can see that in potassium we have all these planes. We do have D values decreasing with the higher Miller indices, and then the intensity also. But if we go here, then we see that potassium chloride do not have few lines which are very low in intensity, and we could not see those lines because those lines are within the background noise. So therefore, we do not see exactly the potassium chloride and its counterpart potassium chloride do not have the same powder pattern. Similarly, the potassium iodide. The position and d-spacing vary because the unit cell. Why it vary? Because it's the unit cell way. Unit cell variation also varies the position and d-spacing. And are of different size. Therefore, a parameter in the d-spacing equation varies. Intensity differ because different amounts with different atomic numbers, atomic powers of the three materials, even though the atomic coordinates are the same for each. What it said that cell in the unit cell, the atomic position may be same, but then the size of the atom, etc., do have different intensities, and thereby the powder patterns are different. And you can see that extreme examples. What you say that KCl, that KCl has 111 has almost no intensity, and 311 is almost no intensity, or too small to be measured. Okay, then we go to the next slide. Okay, analysis of X-ray powder pattern data of unknown crystalline solid materials is very straightforward to identify unknown solids if we have a library of standard. And you see, ICDD, International Center for Diffraction Data, USA, has a very valuable reference sources, which we call PDF, powder diffraction file. We say that unknown solid characterized by unique powder patterns, like we have our characteristic fingerprints. How we developed this library? In 1936, Hanawalt first initiated classifying X-ray powder patterns. What he did, he used d-values and relative intensities to characterize powder patterns. He and his colleagues succeeded in collecting about 1,000 data sets. This has been taken by 1941. From 1941, the American Society for Testing Materials was in charge to standardize this data file and publish this data, and known as ASTM index file. This in 1969 has been changed, and we call it now Joint Committee on Powder Diffraction Standards. This Joint Committee of Powder Diffraction Standards, as well as it's known as PDF, include X-ray patterns of elements, alloys, inorganic compounds, minerals, organic and organometallic phases. I would say during 1990s or till 1990s, so we had a rather strenuous and time-consuming to analyze powder pattern, because we were doing it manually, and matching with the PDF was rather critical also. But we now get commercial and free software. Many commercial and free softwares were available to identify the unknown crystalline materials. Therefore, it becomes relatively easy to do the job. You see, we can, if we superimpose powder patterns of two or more samples, we immediately can identify these, which are the peak for which sample. So, for example, we have an X-ray powder pattern of two materials. One is aluminum nitride and another is silicon. You can see we easily can identify the silicon pattern. Here's the silicon pattern, and this is the aluminum nitride pattern. It's an hexagonal system, aluminum nitride, and this is silicon pattern. This is again aluminum nitride, silicon pattern. We can identify this now with the help of the softwares I mentioned a little bit earlier. Now, we talked about powder diffraction file, but how it looks like, that is also important to know how it looks like. At present, we have about 300,000 materials PDF file, and it is interesting to note that new entries are added to that current at a current rate of about 2,000 per annum, and this is a powdered PDS card or PDF file, we would say, for a sample sodium chloride. What are these in this table? We have to know these also. That table 1, the column 1, this is this one we are talking about, and this is the file number. And then we have 2 in column. There are three strongest D values and relative intensities. 3 strongest D values and relative intensities. And then this 3 is the D values of the lowest angle. This one. Okay, and the number 4 is where we write the name of the materials and its minerals name. And then a very important point to note, in the card there is a star mark in here, and in many cards we see that there is no star mark, it's a C, there it is written C, or it is written O. What does it mean? The star means it's a high quality data. I said a few minutes ago that we have to have high quality data to analyze it properly, powder diffraction. So this means the data presented in the card is a very high quality data. If it is C, that means calculated data from single crystal. It's not powder pattern. It's a calculated data of powder pattern from single crystal data. That means we determine the structure by single crystal, and then what we do from the structure parameter, we can calculate the data. So if it is C here, that you have to remember that it is not powder diffraction data. It's a calculated powder diffraction data from single crystal data. And if there is an O here, it means that the data shown here is low reliability data. Okay, and then this what I talked, and then fine. We in this column, what we are doing, experimental condition, how we did the experiment. For example, we will say about the excess source and the quality, is it monochromatic or not? That's what we mentioned. And then what is the filter used in it, and what type of diffractometer we used. And then what is the reference? From where did we get this data? That what is in this row. And then this is the physical data. That means is it a QB system or what type of crystallographic system, and then its space group, and then its cell parameter, etc., and the crystallographic density. These are given here. And then 7th is optical data, which is not very important for those who are doing X-ray crystallography. There it is. And then last one, the 8th one, is what type of reagent we used for preparing this sample. That's what it is given here. And these are the D values and relative intensity, and then H-Gale value, Miller indices of these values. This is what powder diffraction file or JCPDS card shown to you. Okay, then we see another card now. And this from 1984 onwards, what we did, the other item numbers 2 and item number 3 in previous card, we omitted that. What we omitted that, you can show this item number 2, item number 3 is being omitted in from 1984 onwards. And this card is now the current PDF card. And there are, as I said, there are many sets. So, say for example, the current inorganic search manual, that is 1986, contains about 40 groups. Each group is referred by a pair of numbers. This is the pair of numbers, that is 2.84 angstrom to 2.80 angstrom. What does it mean? That all substance having their strongest D value between these included in this group. That is how we arrange them. That is a very valuable resource point for analyzing powder pattern, unknown powder pattern. Okay, what applications do you have on X-ray powder pattern? Qualitative identification. We can phase analyze qualitatively. For example, I can explain it a little bit. I have a sample. I just take a powder pattern and match it with the already available PDF file, and then see whether which kind of materials it is. But then we can also, what we can do, we can also quantitatively analyze the concentration of each phase present in multi-phase specimen. Okay, and that is what we have to do. And then with the unit cell metrics, we can also determine the size and shape of unit cells. The crystal matrix can be determined. They refined it very in high accuracy, and because the lattice parameters of materials changes with chemical compositions. Okay. Finds widespread in solid solution. So when we have solid solution phase diagram and measuring the true density of materials, we can do these by powder analysis. Orientation distribution functions, we can find out the crystallite orientation in polycrystalline materials by powder function. Residual and applied stress, we can measure the strain present in the crystallites. Simple. Microstructural features, then polycrystallites are using crystallite size, microstrain within crystallites, defects, densities may be determined also. We can also do in situ experiments, that is, we control gas, atmosphere, temperature, and pressure while taking powder pattern and do the synthesis of the material. Full structure solution for powder pattern. The application listed above are strictly for polycrystalline materials. So, but we have to find it that we can do only powder, X-ray powder pattern of crystalline powder materials, polycrystalline powder materials. If it is amorphous, the analysis can be done with other experimental techniques, but not with the X-ray range. We cannot characterize with X-ray the amorphous entirely. Okay. Profile fitting and Ritfel analysis. That's what is a very important analysis we do. Hugo M. Ritfel, who in 1969 applied this analysis for neutron diffraction pattern. So you can see that we can also have neutron diffraction pattern and analyze the structure. So Ritfel, a Dutch crystallographer, and he did it. Now people are very often using this analysis. And with this slide, I will conclude and then take rest in the next lecture. Ritfel refinement is conducted by fitting a calculated diffraction pattern to the observed pattern. What we do, and we can always have a pattern, calculated pattern, and then we have also the observed pattern. Yeah. And then this fitting is done, and we call it tweak pill refinement. That means we are refining it. That in our case, the structure should be known. It is a known structure. We get a structure, a model of the material or crystallite, and then we refine it and find out the true model or true structure. The input data in refinement, what should be the input data? The raw material, the space group, atomic intensity, site occupancy, and lattice parameter. That should be the input data. And what then do we do? By using Gaussian and Lorentzian convolution, we refine it and get as close as possible of the calculated observed pattern. Do we have one? I show one. This is a ritual refinement of barium zirconium powder. You see, this is the dotted one is calculated one, and then the dashed one are the observed one, and the different steps is here there. So we'll come to it again in the next lecture, a little bit of ritual refinement more, and then using high temperature X-ray powder diffraction, how we collect data and analyze the data. Thank you very much for your patience. I hope to meet you in the next lecture. Thank you once again.